En ligne, vous êtes bon? C'est bon en ligne? Okay, so I will say a few words in French and then in English. Donc ce n'est pas nécessaire normalement de présenter Christophe dans ce laboratoire où il a longtemps sévi, mais c'est quand même un immense plaisir. Christophe est mon frère numéro 1 sur Google Scholar. Je vous laisse deviner qui est mon frère numéro 2. Je vous laisse deviner qui est mon frère numéro 1. Donc, on a eu beaucoup d'aventures ensemble. Christophe a écrit la première version axisymétrique et la seule, d'ailleurs, je crois, du code Surfer, qui était le premier code volumofluide. Donc, et il l'a fait pour faire de l'impact et il continue à faire de l'impact. Mais il a fait beaucoup d'autres choses entre-temps que je n'aurai pas le temps d'expliquer, mais il en dira peut-être quelques mots. Donc, Christophe, c'est un grand plaisir de t'accueillir. Je vais refaire la présentation en anglais. So for the English speaking, it's a great pleasure to invite Christophe Josserand, who is a very long-time collaborator. He is my number 2 brother on Google Scholar. And I let you guess who is the number 1. And he has worked on many, many different things, but one of my fantastic memories is when he adapted one of my very first volume of fluid code, the Surfer code, to make it axisymmetric, already to study impact. And he had done many, many different things before. And including for those I know who are English speaking here who are interested, he has worked a lot on contact lines in the framework of what he's going to talk about. And so it's a great pleasure to welcome Christophe. Please start.
Okay, thank you very much, Stéphane. It's also a great pleasure and honor to be here. So I will actually discuss, so the title of my talk is Weighting and Icing, and I will discuss work that started here about 10 years ago, a little bit before 10 years ago. I put some of the collaborators directly related to what I will present here, but there are many others which are some of them in the room that was involved in this general problem of solidification and capillary flows. But here we discuss more the problem of weighting and icing. So as I say, it started more than 10 years ago with Thomas Seon and then Accelerator. So I made the 3 labs that are concerned, so LadHyX, D'Alembert. Even if Thomas is not here, I think everything started at D'Alembert and now Axel is at MSc. So maybe the general context of what we started to do with Thomas more than 10 years ago was questions about solidification and freezing of flows. The question was really to say, okay, we have done some work on drop impact or free deformation at the capillary scale. What happens if you couple that with a phase change, and particularly the liquid-solid phase change? So, and you can see that rapidly there are many solutions you can think about that. So the formation of ice morphogenesis, which is actually the thesis subject of Eli that we'll define soon. You have also maybe in lab formation of stalactite and stalagmite. There are some applications related to that. For instance, the formation of ice on planes and on structure can be very damaging. It can even lead to the crash of some planes. We have also clearly in the environmental let's say application, you can think that more and more the permafrost or pergélisol is melting more, and you have issues about the evolution of the soil due to these things. Here, this is the first work we did here actually with Elisabeth Gabache, which has a simple work of dropping back on the cold substrate, and it was then freezing, but then the ice structure was formed by the impact at 0 Celsius. You know, the phase change between liquid and solid is done at the melting temperature. But since the substrate was much cooler than 0 Celsius, at some point you had the formation of cracks because the ice that was formed at 0 Celsius degree was somehow had some elastic constraints that make it cracks. Few images of some work we did. So there is the PhD of, so this was a work by Elisabeth, the PhD of Virgile, Rodolphe, here also Antoine Monnier, so people that were basically located here. but the question about weighting and icing can be put in a very simple sentences, which is, does water wet ice? So it is a very simple question. So basically, if I have water and ice, if I put water on ice, does it spread? And if it would wet, it would spread maybe to infinity, or does it not spread? So we have some clue about things. So for instance, if you look to a drop solidification, so I think that was taken from the PhD of Lila Segui here. So you can see that even if it's not a water droplet here, I think you can see that definitely the fact that there is a solidification front, so the substrate is cold, there is a solidification front that is growing, you can see that somehow there is a contact line here, or there is an angle between the liquid and solid part. Here, this is just the spreading of a drop. I will come back to that later on. But maybe in the literature, it has been noticed long time ago that if you put a big amount of liquid on a cold substrate, you can see this type of things where you have the ice that is formed, and on top of the ice, you have some water that is retracting on the ice. So in some sense, everything shows that in this situation where you put basically water on a cold substrate, and we see that from the thesis of Virgile. So you see here you have the impact of a drop on the cold substrate. So the impact, I will run it again. At the impact, the drop is spreading. As it spreads, you have a very thin layer of ice that is created. But on top of this layer of ice, you have still water, and the water is retracting. So this movie clearly would tell you that water dewets ice. So in this situation, this water is dewetting this ice. So Knight that did the first maybe observation of that at the capillary scale, at our microscopic scale, also did some experiment where he was showing also that water would dewet ice. So maybe a short, a long story that I will try to make sure. Why is it not so obvious, and why is it not so maybe expected, or why is it surprising or interesting to study that? So basically, the dynamical observation, experimental one that we do with drops at this scale, shows that some water is dewetting in the sense that you have a contact line that is retracting on some ice. Nevertheless, when people try to measure the contact angle of water on ice in this situation, you could see things going from 0 Celsius degree to 40, degrees to 40 degrees as the contact angle. So the contact angle being the angle of the water on ice. And also, I like to say it maybe in simple words, but dewetting its own solid is not the classical situation. So let's say if you look, for instance, to liquid metal, most of the liquid metals, they wet their own solids. So actually, this is not that obvious that a liquid should dewet its own solids. And if you make very simple thermodynamical agreement, you could say, okay, at thermodynamical equilibrium, and I will come back to this important point, you expect that the internal energy of the liquid and the solid are the same. So, okay, we are concerned also with surface energy, but it's not totally clear that you should dewet your own solids. And that comes back to my second point. Somehow, the question itself is maybe ill-posed. That's why maybe it's not easy and you have a lot of questions. So in some sense, when you put a liquid on a different solid with air outside, then you have a contact angle that you can measure. When you have the same liquid, is the same elements and the solid, then you have always to ask the question, do I reach a stationary regime or do I reach an equilibrium? Particularly, maybe the question has only a sense in that case if you are at the thermodynamical equilibrium. That means you are at 0 Celsius degree, the melting temperature, and you have also the pressure of the vapor is exactly the one at saturation. So maybe this situation has a sense. All the other ones, they are somehow out of equilibrium. So then somehow the question that might be the one to think about theoretically is this property at thermodynamical equilibrium. Why all the experiments that I have shown you where water was dewetting ice were definitely not at equilibrium. And actually, this is a question that has been addressed by many people, particularly in theoretical physics, where they basically have shown that somehow the question that is related to that is what is the first layer? What is the first layer of a solid? You know, when you are the first layer of atoms at the solid, is it already solid? Is it still moving particles. So there's this idea of pre-melting layer that maybe there is no, you cannot have a solid that goes until its own surface, and then you have liquid, and then you have ice. Maybe you have something in between, which is a pre-melting layer, which can be at the level of the atomic scale, where the particles are moving. They can be considered as liquid, maybe it's at smaller scale. So there are a lot of work, and actually it's a world by itself that we have been facing when when submitting our paper, and really it's something very, very subtle, and I will try to explain you what is maybe observed by people interested by that. Typically, you can have this type of observation at very small scale, so you are at nanometer scales, where you can see that there is a pre-melting layer which is of the order of few nanometers, on top of which you would have droplet that shows a contact angle with this liquid layer. So in some sense, there is not really the situation that we have in mind, that there is a liquid which is on top of a solid, might not be totally the correct one. Maybe the liquid will be on top of a layer which is a solid plus a pre-melting layer, which is very similar to what Josserand proposed for the moving contact line, where you have kind of a precursor films. So the situation is quite complex, and maybe a way to discuss that again is to look to maybe the classical Young-Laplace or Young equation, where what is the contact angle when you consider a drop of liquid on a solid surface, if it makes an angle. So if this contact line makes an angle, you should have a relation like that, saying that this is the surface energy. So surface energy of ice with the gas, the surface energy of ice with water, and the surface energy of water with gas. And if you have an equilibrium with a contact angle theta, that means that this energy should respect this relationship. So apparently, if you are able to measure the three energy, then you can measure the contact angle theta. So first things, we have no clear, in the literature, there is no clear measurement of these quantities that makes that you can definitely define the contact angle. But the situation is actually more complicated, and it will relate to that. It is that in some sense, this thing is a very simple idea that somehow you have only three surface energy. But another question you can ask yourself, which is maybe here, is what is the energy of a film of a given thickness? And in that case, you have to integrate a lot of energy, like the van der Waals forces, and the van der Waals forces might depend on the thickness of this liquid film. So to make it a little bit short, what is obtained by this calculation is that if you have a very thin liquid film, few nanometers, then the energy is such that the contact angle should be zero or very close to zero. So somehow at very small scale, very thin liquid film, they might wet the solids, but as long as you want to go at a higher thickness of the film, it dewets. So there is something strange which makes that you may have a very thin liquid film that is almost wetting or very close to 0 degree, but if you have more liquid, then you have some instability that creates these droplets. So you see the question that seems simple a priori is not at all easy, and as you have seen, these questions only have a sense when you are at thermodynamical equilibrium, which is far from what we have shown before. Okay, so the question we had actually, and that was definitely the general subject of the thesis of Rodolphe-Grivet, was okay, can we think about experiments or theory about testing this idea, or testing the contact angle, or testing the wetting properties of water or ice at our scale, the scale we are working as fluid mechanics, which is the capillary scale, let's say, or micron, but not below micron. So the idea is, can we imagine experiment at capillary scale that can investigate weighting of ice-water system? So the question we immediately have, how far will be, are we able to do these experiments close to thermodynamical equilibrium? So our idea was to do an experiment and then to make these experiments, try to make all the conditions going towards the thermodynamical equilibrium to see whether we can define a limit of observation in the limit of thermodynamical equilibrium. In some sense, thermodynamical equilibrium is very hard to reach because you need 100% of humidity, for instance, while another one which is maybe easier to reach is the thermal equilibrium, which is definitely, this limit is probably the one that of interest for practical application when you have drops on ice at a normal condition. So thermal equilibrium is much simpler. You just want to see if you can see something or observe something in the limit where you reach the melting temperature. So in that case, you will have thermal equilibrium between the two phases. You will not have yet the thermodynamical equilibrium because you won't have the 100% humidity a priori. And the two experiments we have imagined, actually Rodolphe proposed, is the freezing meniscus I will study first, and then the droplet deposition. Okay, so let's go to these two experiments and see what we have obtained. So the first one is the freezing meniscus. Actually, not exactly that. You might know, I don't know how much you know about moving contact line or contact line, but if you there is a famous Landau-Levitch theory and work, which is say that if you have a liquid which has a finite contact angle with a solid, so if you take a plate and you withdraw a plate at constant speed, you have two types of situations. So if you have a very, very low velocity, you see a meniscus like that. And the height of the meniscus, as we see, is related to the contact angle of this meniscus with the solid. And if you go at higher velocity, there is a velocity above which you entrain the film, and this film is called the Landau-Levitch film. And this was a subject of many, many studies. And just to understand the application of that, this is very important for coating, and it was particularly used for photography at the old time of real photography. If you basically by the theory of Landau-Levitch shows that if you know the velocity at which you withdraw your plate, you know exactly the thickness of the film that you entrain. So if you want to have some physical chemical treatment, you can definitely control that. Okay, so maybe a few words about that. Actually, the work of the meniscus. So the work of the meniscus is the meniscus is simply you take a glass of water, you put water on top, and you will see that there is a close to the boundary of your glass, there is somehow a liquid that if it goes like that. So in that case, the plate or your glass is a little bit weighting in the sense that the water would like to go to be more in contact with the solid, but gravity gravity is in the opposite direction, so you have a finite solution like that, which is called a meniscus. Actually, that was already computed by Laplace, and actually the formula that is from the paper of Laplace, where he basically showed that in the static configuration, so no motion, the thickness of the meniscus, the height of this meniscus is a direct relation with the contact angle. So if you are able to measure the height of your meniscus, then you have the contact angle theta e, so with this relation, so d, which you don't see, is equal to 2 times sinus of 1/2 of theta divided by square root of 2 lambda, which is, in that case, I think should be a capillary length, something like that. Okay, so the important information is that if you, in the static configuration, if you measure the height of the meniscus, you have an inverse point that gives you the contact angle at equilibrium. And importantly, the most favorable case for weighting, which is the contact angle being equal to 0, contact angle being equal to 0 means that you have total spreading, so you have the full spreading. In that case, for the meniscus, since you have to fight against gravity, the height of the meniscus is square root of 2 times the capillary length. So somehow you cannot see a meniscus above square root of 2 the capillary length. Okay, so now let's investigate the situation, the moving situation. So now the same plate, you just withdraw it at a constant speed up, and you observe the situation. So experimentally, what do you observe? Is the velocity small enough, you still see meniscus, and actually you can, actually that was done by Eggers in 2004, you can relate that the thickness, the height that you measure, so somehow there is a contact angle, an apparent contact angle that is observed, and this apparent contact angle is a function of the velocity, put dimensionless by the capillary number, and somehow then you can relate the height of the meniscus to the capillary number, and you have something similar to the static case when your meniscus that you entrain reach square root of 2 times the capillary length. The apparent contact angle is 0 degrees. That means that if you go a little bit above this velocity, you just entrain the film because there is no more possibility of having a contact angle. And if you are above this critical velocity, then you have something which was explained by Landau and Levitch, which is that above this critical velocity, when the apparent contact angle is 0, you entrain the film, and the thickness of the film is proportional to the capillary number to the 2/3. Okay. So now the situation we want is, can we do the same experiments, but with ice formation, with freezing, with a freezing condition? So the first idea was to put a plate at very cold temperature and to withdraw it. But in that case, you know, you don't have a stationary regime. So the idea of Rodolphe was to withdraw a plate at constant speed, and this plate is a Peltier modulus that pump a constant flux of heat that is withdrawn from the liquid. So you have a plate that moves at constant speed, and since it withdraws some heat at a constant rate, it has the speed of ice formation that goes like QS. So you have two velocities now involved in this problem. One is the withdrawal velocity of the plate. The other one is the growth velocity of the ice layer in this regime. So the idea is to reach, in that case, a stationary regime. And you see, so the experiment is this one. So you have to control as much as you can the temperature of the liquid to be as close as possible to the melting temperature. We don't control the humidity rate, so we are not at 100% humidity rate. But you can control the temperature of the water. And you have two now control parameters. One is the withdrawal velocity, and the other one is the ice growth velocity. So we use an infrared camera, and here are what we observed. So this is a typical experiment done with an infrared camera, where we measure the temperature as function of the vertical direction. And this is for the same experiment, so one withdrawing velocity and one ice velocity formation. Very interesting, and this is for different times. So first thing, we observe a steady regime. So that means you withdraw at constant velocity, and you have a steady regime, which is what was expected, because you have a constant velocity of the plate and a constant velocity of the ice formation. More interestingly, we can observe three regimes, which are based on the temperature. So there is one where the temperature is above zero, which means that what you are filming is the bath. There is one here where it varies very rapidly around zero, which is the meniscus. And then below zero, starting from here, you have the temperature are below zero, which is that you are in the solid phase. So in this regime, you can see here you have only ice. So the plate is out of the bath. So now you have only ice in contact with the air. Here you have the meniscus regime, and here you have the bath regime. So, as I told you, with this system, I can control the speed at which I withdraw the plate, but I have also control through my Peltier modulus of the speed of growth of ice. This is not a direct control. With your Peltier modulus, you just put some power. And how can you do that, actually? And I will not go into the detail, but it is interesting to observe that the region where the ice is in contact with the air, so this region, is a very simple situation where maybe you can see that here. Here you have the meniscus, here you have the ice, and you have the constant velocity. So as long as you are here, the ice is in contact with the water, so that means that the temperature imposed in this regime as a constant gradient, and you reach here the melting temperature at the contact between ice and water. As long as you are in this region, you don't have any more the contact of ice or water. So now you don't have any more the melting temperature as the boundary condition, but you have that the gradient of the temperature is equal to zero, because air is mostly you have no thermal diffusion in the air as first approximation. So now somehow, starting from this point, you have a linear temperature field that relaxes, starting from that to another temperature field that has a zero gradient in that case. And this is a self-similar solution. And by measuring, then you can solve this problem with this boundary condition, and you can find a self-similar solution of that. And measuring then the temperature of this point, you can, by inverting this self-similar regime, measuring sigma. So this is a little bit tricky. I can give you more information about that. But basically, measuring the temperature field in the ice region here gives you a direct measurement of sigma, which is the heat flux here, which is related to the ice velocity. So now we have an experiment where we have a very good control of the withdrawn velocity of the plate and of the velocity of the ice growth. And here are the results that we obtained. So as I told you, measuring the height of the meniscus is another way to measure the contact angle. So here are the experiments. They are so I measure the height of the meniscus divided by the capillary length. So square root of 2 is exactly this blue line. So square root of 2 is the limit where if you would have no solidification, you could not have a meniscus above this length. And in some sense, we measure that as function of the speed growth of the ice. So horizontally, it's speed growth of the ice, and every curve is for different withdrawn velocity. So let's go a little bit simple. let's do it in a simple analysis. So let's consider this curve, this red curve here, which is a constant withdrawn velocity, but I increase the ice growth. What do I observe? I observe that as I increase the ice growth, I diminishes the height of the meniscus. And we can understand that clearly. I withdraw some liquid, but this liquid is also eaten by the ice growth. So as the ice growth is higher, as I cannot go, as I go lower. So the higher the speed growth of the ice, the lower is the meniscus. If you do the other things, if you go in that direction, so in that direction you have a constant ice growth, but you increase the speed of your plate. So as you increase the speed of your plate, you go to higher meniscus because you withdraw your plate. Interestingly, most of these experiments are above square root of 2. That means for most of the experiments that we considered, if we wouldn't have had solidification, we would have a Landau-Levitch film. Only few of them are below that, so only few of them might not be in the configuration of Landau-Levitch film. On the other hand, why, as we have a Landau-Levitch film, in this case, we don't see a Landau-Levitch film, just because since you are your ice that is growing, you withdraw a film, but this film on the same time is eaten by the ice growth, and there is always a final height at which you have no more water. Okay. Can we put that a little bit more in numbers? So as I told you, the thickness of the plate, when you are above square root of 2, the thickness of the liquid layer that you withdraw is proportional to the capillary diameter to the 2/3. And now you know that this thickness is eaten at constant speed, at a constant speed by the ice. So you have, you have basically a velocity of the ice that is proportional to that. And if you just make the balance between that, you have a prediction that the height of the meniscus above square root of 2 is simply proportional to the capillary number to the F divided by the ice growth capillary number. And if we draw all our data, we have a very nice alignment of all our data along this line with a prefactor of 0.94, which is amazingly the same prefactor that was given by Eggers in his theory without solidification. And you can see that there are a small region here where you are below, which are the region where you are below square root of 2. So somehow the situation above square root of 2 is well understood. When you are above square root of 2, you withdraw a liquid film of a given thickness, and this given thickness is eaten by the growth of the ice front. Okay. So as you know now, somehow what is of interest for us is, or maybe I can go back. So somehow I treated most of the data here, and I will focus now maybe on this data. The ones that are below square root of 2, they should give us some information of the contact angle, because this one, they are really an equilibrium between the withering plate, the ice front that is growing, and the boundary condition at the contact line. So these few points, maybe you should contain some information about the moving contact line, or the contact angle of the water and ice, while this one somehow will not give us information on that. Okay, what can we do for that? Maybe let's write a little bit the equation. So for the static meniscus equation, if you balance basically capillary forces with gravity, you obtain a simple equation, which is the derivative of the curvature of this curve is equal to 1, and then you can solve that and you obtain this relation. If now you add withering of the plate, you change your equation is almost the same. So without velocity in the liquid, you have the derivative of the curvature is equal to 1. And now you have the balance. The balance is not only between gravity and capillary force, it's gravity, capillary force, and viscous force inside the film. And if you put that, you obtain this equation, which was studied in detail by Eggers. And somehow this, if you just put the problem of the contact line is that you have to put some slip lengths here to make this equation solvable. But again, if you fix yourself a slip length in your equation, you measure a contact line 8, it will be a direct function of the contact angle and the capillary number of the withdrawn. Now, if you add solidification, you just now change this equation into this equation, where basically the same one, except that now you have to consider that part of the liquid is eaten by the ice, and somehow this equation is a mass conservation equation, so now you have to withdraw here. And in that case, no, sorry, I did something wrong. Here, without solidification, sorry, I was too fast. Without solidification, when you have the Landau-Lewis film, you don't have any more contact line. You just have a film, and the solution of the film is this one, G being the flow that goes inside the film. Sorry. Now, if we add with solidification, what is the solution you have? So, without solidification, you have this equation. If you want to solve a meniscus without solidification, you have to solve this equation with this boundary condition. So, at z equals 0, h equals 0, the derivative, sorry, here, at h equals 0 is 0, h prime is equal to the contact angle here, and at infinity, you have to, h goes to infinity. When z is going to ZCL, it goes to infinity. So, now, without entering the detail, if you add the solidification, you add exactly this term. So you have exactly the same equation, except that now you have to withdraw in this equation the fact that part of the liquid is eaten by the ice growth front. Very interestingly, this term is proportional to z. So it explains also in the equation why you cannot have any more a liquid film, because there is always a z for which this term becomes negative and there is no more possibility of contact line. So this equation somehow is reminiscent of the fact that you have only meniscus in this case, you cannot have a film. So now we have to solve this equation. So the derivative of the curvature is equal to 1 plus this term, which is a little bit ugly with z. And it has to be integrated with specific boundary condition. But the idea is that if we can solve that, if we fix ourselves CIP and CSS that we take from the experiments, we measure in the experiment ZCL, and then there is only one theta E as a boundary condition that can give us the good ZCL. So somehow we have a numerical, so we'll do numerically solving that, and somehow for each couple of CAS, CAP, we have only one theta E that give the correct ZC. So that's exactly what we did. So the numerical integration of this equation is quite tricky, and that took some time at the end of Rodolphe's thesis. But basically, you have to solve that. So you basically you give yourself CAS, CAP, then you vary the contact angle until you find the good ZCL that you measure experimentally. In some cases, the equation can have a very nice structure where somehow you start with, here this is close to the contact line, so you start with a theta E times Z, but then you, at some point, you reach the region where that is exactly the linear term. So here you have in this region, you basically have something which is tangent theta E times Z, but there is a region in the domain where you have exactly this term that is vanishing. So Z over H is exactly the ratio between CIP and CAS. This is this regime, and then you have again something that goes to the bath. Okay, so the details of this solution are quite tricky, but the important thing is that numerically, if we give us CAP, CAS, and we measure ZCL, then numerically we can make an inverse problem trying to find what is the contact angle that we need to obtain this height of the meniscus. So by doing that, here it is what Rodolphe obtained. So basically, when you are above square root of 2, you don't see any dependence on the contact angle with the height of your meniscus, which is reminiscent of the fact that when you are here, you are not in the regime where you have static meniscus. What is interesting is when you are below square root of 2, you have a clear dependence. So if we measure ZCL here, that means the contact angle is this one. If we measure ZCL here, we have this contact angle. So now we have a direct measurement of the contact angle as we measure the height of the meniscus below square root of 2. And if we do that from this data, here is what we obtain. I will go a little bit fast. We obtain exactly this thing. So for the few experimental data that were below square root of 2, we are able to measure some contact angle. So you have a high variability, but basically we measure a contact angle which is, let's say, about 8 degrees. And what is interesting is it almost does not depend on the high speed front. So in other words, if we can consider that there is a limit where that goes to 0, and where that goes to 0, you are reaching some thermal equilibrium. So there is a limit. Okay, we don't have exactly the point here, but this experiment suggests that there is a contact angle of water on ice in the limit of thermal equilibrium that is, okay, around 6, 7, 8 degrees. Okay, so that's first things. I will do a partial conclusion, maybe go faster for the rest. So basically, interesting thing, we have always a stationary regime when you have receding contact angle with freezing. The height of the meniscus is a direct way to measure the contact angle. using numerical resolution of the equation for the meniscus, we can deduce theta e from the measure of ZC. And we have, I show you rapidly the numerical simulation, but we have very interesting matching to do for this equation that we haven't done. And actually, we have submitted that. And the result of 8 degrees is very similar to other paper by other authors. So now let me go in the last 15 minutes to the second experiment I told you. So somehow the idea is, so we have one experiment that suggests that there is a contact angle which is non-zero, which is more about 8 degrees than 0. Can we do another experiment? So the other experiment is a drop deposition. And actually the drop deposition is, let's say, a road subject where people somehow try to take a drop of water and they make the drop of water in contact with a glass plate, and they observe, so here the glass plate is above, they observe the spreading of the drop on the glass plate. This was done in the PhD of Anne Norbiance. And what is interesting is that the short time dynamics of this spreading can be understood as square root of time. I go a little bit fast just by making the balance between the capillary force that wants to extend the drop, while there is inertia that is balancing these capillary forces. If you are in the regime where the water is totally wetting the substrate, you expect that after this regime there is a later time regime that goes to t to the 110, which is called the Tanner's law. And if you are not in the case where you are totally wetting, this square root of t should stop at some angle, at some final radius that give you the contact angle of your dynamic. So when you have a drop in spreading on a substrate, if you have no freezing, in the case of total wetting, you should wait to infinity with a very small growth rate at large time. And if you have a finite contact angle, your spreading should stop at the given radius. And again, measuring the radius of your drop is a way to measure the contact angle of equilibrium. Okay, so this experiment somehow, without freezing, is a way to measure the contact angle of a liquid and a solid. So again, the idea is to do that experimentally. So that was done also by Daniel and Vladimir. And basically, the idea is to put a drop of water on top of a very thin layer of ice, where you control the temperature of the ice, you control the temperature of the drop water. You also try to control the atmospheric condition. But in that case, we were trying to avoid frost formation of the substrate, so we had very low humidity rate. We are not in the limit of high humidity rate. And okay, and we have all the observation. So we did vary the radius of the drop, not a lot, but the droplet temperature close to 0, the gas temperature also close to 0, and the ice temperature from 0 to minus 20 degrees, and we have a lot of experiments very close to the melting temperature. Maybe let's show some experiments. So the first one is what we call cold ice, so minus 10 degrees. So basically the drop is spreading, and it stops. And it stops at some finite radius, showing clearly a contact angle. Here we have very cold ice, so it's not at all clear what is the arrest dynamics. Is it due to the solidification that somehow pin the contact line, or is it because we reach some contact angle? What is somehow more interesting for our discussion today is the second experiment where we do that at minus 0.16 Celsius degrees, so very close to the melting temperature, which is 0 Celsius, as you know. So here you have the same short time dynamics. The drop spreads rapidly, so maybe something close to the square root of t relation. But then, and I will accelerate the movie, you can see that it continues to spread. And it stops at some point. Oh, sorry. So somehow the question is that we see that after the rapid spreading, there is a very long spreading. So somehow the question, we can summarize the question, is this long time regime a t to the 110 regime which will go to infinite spreading if there will be no solidification? So is it stop because solidification is stopping the contact line, or is it stop because we reach a contact angle? So that's why we will try to investigate. So somehow we see that there is a long spreading, so which means that there is probably a very low contact angle of water on ice. But is it 0 or non-zero? And for that, we need to know whether the final arrest is due to solidification or to have reached the final contact angle. Okay, so for that, they measure a lot of, so the radius as function of time, and you can see that at short time, you have this very nice square root of time regime. As you vary the temperature, you can see that the square root of time goes to larger and larger time. So basically, for cold ice, in the sense -20, -10, even -3 Celsius, the dynamics that we see can be very simply interpreted. You have a spreading, and the spreading is arrested by something which is due to the temperature. So probably in this regime, you are arrested because at some point the solidification of the ice is pinning your contact line. Then, interestingly, there is another regime here where after this time you have a much slower dynamics, which actually, if you try to measure it, is very close to T to the 110, but which is still arrested here. So now the question, is it arrested here because of solidification or because we reach a contact angle, final contact angle? So maybe I will skip that. So here the idea is that we are in the viscous capillary spreading. This viscous capillary spreading would give a T to the 1/10 law if you are in the full spreading regime, and it will give something not a scaling law if you are in the case with a finite contact line. So what do we do? So maybe I go fast on that. You can write actually the equation of the moving contact line of the drop that is spreading. So basically we use a classical law of the moving contact line. So basically the radius of the drop is spreading because what is the force that is pushing it or making it spread is the capillary forces. So the capillary forces tells you that as long as the contact angle that it makes is bigger than the equilibrium contact angle, this force is negative or is positive, sorry. And then you just put all the good data for that. So basically the spreading of the drop is due to the ratio between the capillary forces that wants to spread it divided by the viscous forces that wants to slow it down. And if you do that, you have some variation. So basically, we can solve now these dynamics with a given. We do somehow the same problems than before. We will try to fit this data by finding what is the contact angle θe that can fit it. And we can measure for each experimental things, we can measure the θe that allows the good dynamics of the spreading. And this is the curve that is interesting. So now, as you have seen, with the spreading dynamics that we solve numerically, we again make an inverse problem of finding which is the contact angle that fit the best the spreading, experimental spreading. And we observe and we measure then a contact angle. And we measure how this contact angle evolves with the temperature. This is, I think, the black curve. And the red curve is the contact angle that could be deduced by the final radius. The thing is that -10. Here we are. 0.5. So what is here you see that the equivalent contact angle of So what you obtain is that when you have a cold ice, your effective contact angle is definitely not 0, and it varies with the temperature. So definitely this contact angle here is an effective contact angle that is actually dependent on the complex dynamic between the contact line spreading and the pinning of the contact line due to solidification. But if you are below -1 degree, so between -10.8 to here, the smallest one we had is -0.05, we see almost no dependence on the contact angle that we measure with the temperature. So that means that in this regime, the solidification is not playing any role anymore. So in this regime, we observe that the final stage of the spreading is due to the equilibrium with the contact angle, with the surface tensions at a given contact angle, and not to the solidification. Because if the solidification will play a role, you will have a variation of that with the solidification. And actually, if you measure if you estimate the characteristic time scale, the time scale for solidification goes to infinity when you go to that, while the time scale for the spreading remains constant in this regime. So somehow, again, here we have a proof that in this regime, in the limit of the thermal equilibrium, not the thermodynamical one, but the thermal equilibrium, we have a contact angle of water on ice. And actually, if you measure it, in that case, it is 11.76. So somehow my second partial conclusion, I will go fast on that, and I will do basically using a water droplet, using the same type of treatment. That means we look to experimental results, and we try to deduce from experimental results a contact angle by doing some inverse problem resolution. We can measure a contact angle of water on ice, which is 12 degrees. And this actually has been published, or is published these days in GFA. So let me finish with a conclusion and maybe some perspective. So the two experiments suggest that when thermal equilibrium is reached, there is a dewetting of water on ice at small contact angle, but non-zero contact angle. We observe two different ones. One is more close to 8, the other one is close to 12. So in some sense, we have two different value of the contact angle. So how can we reconcile that? First, I would say that I'm more convinced by the 12 than the 8, because the 8, the inverse problem of the meniscus is quite tricky, and there is a problem with the tip length. So we should look more carefully when we vary the tip length whether it change that. But that's the mathematical aspect. For the physical aspect, for the meniscus, you are definitely measuring a receding contact angle. While for the spreading, you are definitely measuring an advancing contact angle. So if there is an hysteresis of the contact angle, that could be also explained, and it goes in the good direction. You know, the small one is for the receding, the high one is for the advancing. Even if we believe that on very clean ice, you expect to have very low hysteresis of the contact angle, it could explain why the smallest one is observed for the meniscus, the other one. So when we submitted this paper, we had a lot of discussion with people coming from the pre-melting layer and the people doing thermodynamics. So it is clear that we cannot say that what we have proved is that the contact angle of water on ice in the thermodynamical limit is this value. We cannot say that. We can say on the other hand that the contact angle that we measure is the one that you have at thermal equilibrium, which is probably the case which is of practical interest for most of the application. Most of the application, you don't control really the atmosphere humidity rate, but you can be close to 0 Celsius degrees and see what happens. So even if we are probably in the case where it's practical interest, and what is interesting is that all the experiments that were done very carefully show basically contact angle between 8 and 12. So definitely for practical interest, for let's say practical experiments of water and ice at let's say atmospheric condition, we could say that the contact angle close to thermal equilibrium should be around 8 and 12. On the other hand, we don't really answer to maybe the more fundamental question: what would be the contact angle of water on ice at the thermodynamical limit? Are we in the situation where you will have a pre-melting film on top of which you will have the drop making an 8 degree contact angle? We don't have an idea, and this is something we would like to work more, and particularly with colleagues from thermodynamics. And I think that was my thing. And this is my conclusion. Thank you very much.
Okay, thank you very much. There are many questions. Sébastien.
Comment on vérifie que la surface de la glace est si propre, si belle, qu'il n'y a pas d'impureté ou de rugosité? Souvent, la glace, il y a plein de rugosité.
Alors, ça faut plus demander à Daniel qu'à moi, comme tu peux. Alors, je crois qu'ils ont beaucoup travaillé là-dessus. C'est aussi pour ça qu'on a qu'on a d'une certaine manière chassé l'air humide, pour éviter par contre qu'il y ait du givre qui se forme dessus. Donc, du coup, en faisant ça, on n'est pas là. Et alors, je crois qu'il y a eu tout un système il faut la faire croître très longtemps. Tu as aussi plein d'effets vicieux. Il faut que ton eau, quand elle va solidifier, il n'y ait pas de bulle qui se forme à l'intérieur. Donc, il faut que tu aies une eau qui soit. Donc, bon, mais ça, il y a tout un travail, je crois, de faire croître très très lentement. Peut-être vous puissiez refondre. Et alors, de fait, à l'œil nu, mais plus qu'à l'œil nu avec le Navitar, c'était très plat. Ce qui ne veut pas dire que c'était un cristal. Tu vois, on n'en est pas. Tu vois, c'est clairement un polycristal, mais qui très lisse.
Merci. La glace, c'est compliqué par la transition de l'eau. Est-ce que tu penses que faire ça avec des métaux liquides ou des D'autres matériaux, ça pourrait être intéressant.
Alors notamment, on avait réfléchi avec toi parce que, en fait, pour toutes ces histoires d'énergie de surface, c'est assez compliqué. Il y a un bouquin d'Isaiah Joly qui fait ça. Il semblerait que le fait que l'eau soit moins dense, que la glace soit moins dense que l'eau, et pas c'est pas une conséquence directe, mais ça semble quand même être des arguments qui ont dans les sens. Ça veut dire qu'il y a beaucoup d'énergie de type dipôle, tout ça. Et donc il fallait regarder quels sont les autres. Il n'y en a pas beaucoup. Il y a le gallium. Et je crois qu'il y a un truc qui s'appelle des moines. Donc, ça serait une idée, par exemple, d'aller regarder ça. Et puis, mais alors, je crois que le gallium, c'est quand même pas. Je pense pas qu'on soit équipé. Enfin moi, je n'irais pas faire de manip en gallium. Mais bon, moi, je n'irais pas faire. Mais toi, donc, il y avait cette idée-là, mais il faut un peu y réfléchir. Ouais. Mais ça serait une idée. Voire même, toi, je dis de manière un peu péremptoire que c'est bien connu que sur un solide, sur un métal, le liquide mouille le métal, ça mériterait d'être regardé plus près parce que, toi, de refaire peut-être les. Toi, et là, on pourrait faire avec de lait. Ça va faire, tant qu'à faire un métal pur, je pense que c'est mieux.
Et du beurre, de la cire, du chocolat.
Alors ça, il y a des choses qui ont été regardées, typiquement, il y a chez François Boulin, il y a des choses comme ça, mais c'est plus des trucs purs, hein. La cire, c'est un... Donc après, ça peut être intéressant, mais c'est peut-être... Mais oui, il y a des choses qu'ils ont fait avec ça. Il y a des questions en ligne, hein? Puisqu'on est parlé en français. Oui. Alors,
Ils disent lambda parameter in Eggers model.
c'est la longueur de glissement. Donc, normalement, donc, tout liquide, il y a toujours une longueur de glissement. Normalement, elle est, quand tu as une surface rugueuse, tu vas pouvoir faire un modèle qui te dit quelle est l'ordre de la rugosité. Mais même à un moment donné, elle devient à l'échelle nanométrique. Typiquement, là où la mécanique des milieux continue se casse la figure. Donc, mais justement, dans ce qu'a fait Rodolphe, il a pris un lambda qui est très petit, mais qui est de l'ordre du nanomètre. Il faudrait peut-être le mettre de l'ordre du angstrom. Je ne pense pas que ça fasse varier beaucoup, mais après, ça devient. Et alors, ce qui est amusant, c'est que si tu prends lambda égale 0, ton équation, elle diverge, en fait. Sachant que même avec le lambda, la courbure diverge, mais par contre, H ne diverge pas. Enfin, donc, ça, c'est tout le paradoxe de la ligne de contact, hein, qui avait été pas mal mis en avant par De Gennes, enfin, par d'autres avant. Il faut régulariser à petite échelle. Tout est cool.
So to go back to what you were saying precisely, if you have phase change, this can modify the regularization of the contact line. So maybe you have any intuition about that?
That's when we had discussion about this paper with people from statistical physics, they say that maybe what we measure is clearly out of the thermodynamical equilibrium, because since we are below the 100% humidity rate, you have a strong evaporation, and this strong evaporation which puts an extra pressure that could somehow force the system to have a contact layer. Why you would not? So that, for instance, one of the things they say, they claim, okay, be careful. But what is interesting is that even if this is probably present, the fact that it does not depend a lot of the humidity might say that we are somehow in an extreme regime. So as soon as you have a little bit of evaporation, you reach another regime, which is maybe dominated at small scale by this evaporation, but would give a constant contact angle that does not depend anymore from that. So somehow you have a very low evaporation rate that might give another contact angle, and high evaporation rate where you have.
We have some evidence in our own numerical simulations by Tian Yang, who is here, that phase change modifies the contact angle very strongly.
Probably it does, and in the case of water, what is a little crazy with water, you cannot just do that. You have also to put somehow some van der Waals forces to measure that with the thickness of your layer. So, the water is really a crazy, as you say, complex thing, so ice and water. And if you really want to measure correctly all this energy, you need to, for instance, the energy of thickness of water is not the same as another thickness, and it can give tricky results.
Tu as parlé de gamma et de température et pas de marangonie. Je mélange des trucs ou...
Non, alors non, tu n'as pas tort. Il pourrait, ça c'était des questions. Il peut y avoir, on a des différences de langue. Il pourrait y avoir des marangonie. On les a pas vus comme étant dominants. Et à nouveau, le fait que, par exemple, l'angle qu'on mesure in fine ne dépend plus de la température, veut dire que si c'était... Mais c'est plutôt donc on a plutôt des évidences indirectes que des... Tu vois, je n'irai pas jusqu'à dire qu'on a zéro marangonie flow, mais en tout cas, s'il est là, il n'est pas crucial, puisque il devrait dépendre fortement de T, et on ne voit pas de... Mais en effet, il pourrait y avoir.
questions, tu seras un peu là cet après-midi.
Je suis là cet après-midi.